Hello, Happy New Year, and welcome to Office Hours by Bit Gardner. My name is John Kowalski. I'm part of the marketing team here, and I'd like to welcome you to our first webinar of the year. Hope everyone had a nice holiday and had some time to relax with family and friends and unwind. I don't know about you, but we're starting off with a bang here. I have more projects to do than what I know what to do with. So anyway, our office hours format, if you're unfamiliar, it is a shortened presentation, usually 20, 25 minutes-ish on the topic. Today, we're talking color theory, one of the foundations of color. So some great information. If you're new to it, if you like some bit of a refresher, this is the place to be. After the 20, 25 minutes, the floor is yours. If you have questions, comments, need clarification, any challenges you're facing in your own facilities with measuring a color, gloss, anything color related, just log them in the chat box and we'll get to them and have a good discussion. There may be times where we need some additional information, and I'll unmute your microphones and you can unmute yourself then, and we can have a dialogue. So this is about helping you all with your color theory today. We have our expert, Mr. Noah Morgan. He's our application specialist. He's going to be presenting and fielding the calls. What else? We are recording this, including the discussion. So immediately following the presentation, you'll receive an automated marketing message with that link to the presentation. Feel free to watch it later, grab screen grabs, share it with colleagues, whatever you like. Also know that anytime you receive any of the marketing messages, if you have a question, if you need some assistance with anything, feel free to hit reply. It'll come to my team, and we'll forward it to the right applications or technical person like Noah here. So again, welcome. Let's kick it off. Noah, you ready, sir?
Yep. All right. So thank you guys for joining. We're starting today off with a good one. This is our first one of the year. My personal favorite presentation. So let's get after it.
Nice.
All right. So starting off, this presentation pretty much goes over basics of color theory when it comes to visual color analysis, the background information for how that's done, and it can also be used to understand the basic principles of measurement equipment as well. So how do these instruments measure color? And it's close to the same way as how we visually see color. So starting off, you need three essential things in order to see color or to measure color. One being the light source, because without light, there is no color. You need your object, because the object is what the light reflects off of and absorbs into in order to create the color we see. And then we need an observer, somebody there to witness that color. It can be an instrument too to measure that color, being a spectrophotometer. But we need these three essential things in order for color to be evaluated. All right, so starting with light, one of our first essential things needed. What is light? So light is a collection of photons anywhere from 400 to 700 nanometers, and that counts towards the visual spectrum, so colors that we can see. Stuff below 400 nanometers is UV light, so we can't physically see that, but it's still there, it still exists. Anything over 700 nanometers is infrared light. So again, we can't visually see it, but it's still there, it still exists. It can be used in some military applications, but all of this is what encompasses our light. And we see here we have light coming from the sun. You can imagine hitting a prism here, and that gets dispersed into all the colors of the rainbow per se. So why is light important? Light's important because it can be different depending on where we are, the environmental changes. light bulbs, LED lights, everything is slightly different than each other. So when you're trying to evaluate a color, whether it's visual or with an instrument, you need to have a standard set of ideas of what that light source is. So here we have 3 examples of standard light sources. We have D65, which D stands for daylight, 65 means 6500 Kelvin. So that's the temperature of the light. And what that is, it's your standard daylight light source. Next to that, we have A light, so that's your tungsten light. And we see this light is mainly for, or you'll mainly see it in homes, so it's that warm lighting. Next to that is fluorescent light, so usually in an office setting or a department store. Typically, you'll see each of these lights in their own environments. And the problem that we have or can run into is that colors can look different under different light sources. And so what that means is that when you're taking, let's say, a cup that's orange and you have it under daylight, because of the distribution, if you can see here across that remission curve here for daylight, you're having an equal representation of all the colors of the rainbow, if you can imagine, being cast on that object. And so for the most part, it's not going to be extremely vibrant. You're going to see color equally. But if you had it in that A light, because of the higher amounts of red light that's being cast down from that light source, it's going to make that orange cup look even more vibrant, just because of the amount of red light that's being cast over that object versus blue light or orange or green or purple. The next to that was fluorescent. A good example of this is if you had a blue t-shirt under a fluorescent lamp. That blue t-shirt's going to pop because of the spikes that we see here in that remission curve. Whereas something like a red t-shirt is not going to look as vibrant under that fluorescent lighting. So this just goes over some of the standard light sources and what they mean. So again, talking about the light sources, something interesting can happen in many cases, which can be pretty important in manufacturing or production. And that's something we call metamerism. And so what metamerism is when you have 2 objects that will match under one light source, but if you were to change the light source, you'll get a mismatch. And that's usually because of different pigmentation that's used in whatever process or production that's causing that. And so in this case, what you can imagine is one of these cups has one formulation to get to that color, and the other cup has a different formulation to get to that color. But in the end, under D65, under daylight, they both match. But when you bring in another light source like A, which is really strong in the red region and not very strong in the blue region, now we see that there's a mismatch. So what you can imagine is happening is that this cup here at the bottom on the right side may have some pigmentation in it that might be a little more red than the other cup. And so when you cast this A light, which is very strong in the red region of the visible light spectrum, you're going to see that cup appear more red than the other one. Now, if you've ever seen a spectral reflectance curve, and we'll talk about that later on in the presentation, that's what you're seeing in the middle here. So one of the cups is one of the curves and the other is the other curve. And typically you'll find metamerism if you have the spectral reflectance curve cross each other 3 times. Other than that, you'll usually have pretty close to the same color. But if it crosses 3 times, then you can expect to see some metamerism happen somewhere along the line. All right, so that was the light sources. Next, we'll move into the observer. So what's important about the actual observer or the person looking at that color or the spectrophotometer looking at a color. So we'll start by looking at the eyes. And this is important because that's what we see color with. We see it with our eyes. So what's happening inside of our eyes that help us to see this? So we have cone cells and we have rod cells. If you see here, our cone cells make up the RGB colors, so red, green, and blue. And then we have rod cells, which are lightness detectors. And these are used at night to help us understand shades and dark areas and light areas. And we need both of them. That's the very important thing, is that we not only use just the color, the cone cells, but we also use the rod cells because lightness is an important factor in what color we're looking at. Now, when we look at this experiment that was done, and for background, this was done in the 1930s. I believe it was 1932 by two scientists. One was named Wright and one was named Guild. And basically what their idea was, at the back of the eye, I'll switch back to this slide here. At the back of the eye, this region called the fovea, there's a high concentration of cone cells, so just color detectors. And so the idea was, if you were to look through this partition, through this wall, or this hole, this aperture through this wall, and one side you have a color that you're trying to replicate, and on the other side you have a blue lamp, a green lamp, and a red lamp. And the idea is that you're mixing those colors together by different powers in order to create the purple color that you're seeing on the other side of this black partition. And so when you look through this, they're using the small aperture, which equivalates to the 2-degree observer, which was the original observer angle. And what that meant was that they were using the small section in the back of the eye that had the highest concentration of cone cells to detect the colors that they're seeing on one side and replicate that on the other side. And that's how the 2-degree observer was developed. So this gives a better image here. The 2-degree observer is a small section in the back of the eye. And later on, I'll say, more experiments were done, and it was found that the rod cells, again, that detect lightness and darkness, were a better representation of how we see color because it takes into account that full range rather than just looking at the color. And so later on, after many other tests and experiments that were done, it was found that the 10-degree observer was the optimal observer to use when evaluating color, just because you have not only the color parts of it, but you also have the lightness and darkness parts. Today, the 2-degree observer is still used, and it's used in things like printing industry and the ink industry, usually for measuring smaller samples. And the reason being is because when you're looking at something small, as an example, the size of a quarter, it's using the 2-degree observer angle in the back of your eye, versus if you looked at something larger like a tennis ball, it's going to use a larger section of your eye as far as viewing goes. And so as a rule of thumb, if you're measuring something that's the size of a tennis ball or maybe larger, you're going to want to use the 10-degree observer, versus if you're measuring something very small, like, let's say, something that's printed on a piece of paper, the 2-degree observer is more optimal because it's using a smaller section of your eye. And so when you look at some curves according to the 2-degree observer and the 10-degree observer, you see that they don't exactly line up. And so it's really important that if you say you have one plant or one facility that's using a 10-degree observer on their spectrophotometer and another plant's using a 2-degree observer on their spectrophotometer, the values aren't going to line up exactly. And that's just because it's a different type of measurement that's actually occurring. And so if you're having issues with your data collection and you're finding your results with different plants or different locations aren't lining up, it's always a good idea to look at what observer degree is being used, because it could be that one plant or one facility is using one and you're using a different one. And when you line up the data together, you're going to get different sets of data. All right. So we talked about the light sources, the importance of them, what they are. We talked a little bit about the observer angles. So let's go into the object, what's actually happening when that light hits the object. So we have a couple things that occur. If you can imagine light coming down from the sun, it hits a sample here. We have the first reaction, which is gloss. So what that is the light coming down, touching the surface of that sample, and then reflecting off at the opposite angle that it comes down at. Typically, gloss is white light, and so that's your specular reflection. Then the next thing that we have occur is the absorption. And so what that is the light coming down, and the special pigments in the sample there or object are selective, and so they're only going to absorb certain colors of that light. And in this case, we can think, what's happening here is the light's coming down, and this object is orange. And so what's happening is all of the light that's not orange, so blue, green, yellow, red, all of those lights that light is being absorbed into the sample here, and it's diffusing orange. And so to us, this object is going to look orange because that's what's being diffused. A better example is this here. So we have our sun coming down, hitting the surface. We see the sun encompasses all the colors of visible light, from purple to blue to green, yellow, and red. It's hitting the surface. Our purple, blue, yellows, and greens are getting absorbed into the sample using the selective pigments that are used in the formulation. And then we see a diffused reaction of the orange that's being scattered about, and that is what we see the object as, because that is the only color that was not absorbed in this case. And then if you see the specular reflection, your gloss, that's your pure white light that got reflected off of the surface. So that's a nice little overview of what's actually occurring on an object as that light's coming down. And it's interesting to know with any type of color measurement, what you're measuring is that reflection, that diffused reflection. And what's interesting is you're able to get the spectral reflectance curve. What this is essentially the fingerprint of a color. It's saying how much of this light is coming back at this specific color wavelength. And so if you can see from this example, the top left example here is a blue cup. And so what we're seeing is that in the blue region of visible light, that's where we have the most amount of reflectance. And so that's going to end up looking blue. And then in the one next to that, it's a red cup. And so we see a little bit of peaking in the blue region. And then it peaks out at the highest point in the red region. And so we can say that's a red cup there. Below that's green. So we see the largest spike in the green region. And then for yellow, it's a little tricky, but there is a peak at the yellow point that kind of slopes down slightly for the red. And so really it'll be somewhat of an orange color, but it's close enough for this. All right, so once you have your illuminant defined and you have your object reflectance curve defined, your observer angles defined, you can then get color scales. And historically, it used to be XYZ coordinates. This went to a specific color space back in the 1930s. But we've since moved on to a better, more uniform color space known as LAB. And this is what most people are more familiar with these days. And this is an example of it here. But if you can imagine a three-dimensional sphere where you have your lightness value, which is your L value, and that goes from 0, which 0 being black, to white. So white's 100. White is at the very top here. And then you have your A and your B axis. So your A axis at negative A, it's green. Then at positive A, it's red. And then your B axis at negative B, it's blue. And at positive B, it's yellow. And so using those coordinates, you can identify where you are in color space when you're measuring a color or seeing a color visually. It's great system. It's more uniform than the one before. This is what most people use these days. Below that, we see additional values there, your LCH values. What that is essentially, it's the same system, just a different way of finding out where you are. It's a different coordinate system. And what that is your lightness remains the same. It's still black to white, 0 being black, and then 100 being white. And if you can imagine, 50 is around a gray color. And then your chroma, which is your C value, is how far away you are from the 0 point on that graph there. So the more chroma you get, the more vibrance or saturation that color is, the further away it is from the 0 point on the axis there. And then you have your hue angle, which is your H value. And the hue angle starts at the positive A axis and actually goes counterclockwise. Actually goes counterclockwise 360 degrees. And so again, using those coordinate systems, you can find your L value, then you can find your C value and your H value, which is your,
Someone's looking for you.
No, popular guy.
There you go.
You can use all three of those values, your LCH, to find exactly where you are in color space. So you can, again, same system or same idea as LAB, but just a different way of doing it. And the reason for the two there, why there's two different ways of doing it, ideally, LAB is used for pastel or achromatic colors. But as you get more chromatic, we find that the LCH values are better at determining where you are in color space. All right. So here's an example of how you would figure that out. So when we look at this example here, we see an L value of positive 58.12, an A value of positive 30.41, and a B value of positive 36.26. And when we put that on this graph here, we see, let's say our L value is around 50, so we start here at the gray. Then with our A value, it's positive 30. So we're going positive 30 on the A axis, and we see that it's in the red region. And then we add positive 36 to our B axis. And when we look at that, it puts us right about this orange color. And so that's essentially how you would use the LAB system, how it makes sense. Now, if you move on to the next slide, this brings into delta E. So some of you may be familiar with delta E and what it is. It's essentially your difference, usually from a standard and a sample. So if you're trying to achieve a specific color, that would be your standard, your target. And then when you measure your samples to that standard, you're going to get a difference value of how close are you from that target goal. So this is the simple equation for delta E star. So one of the first color difference equations that was developed back in the 60s. What you're looking at, if you can imagine your sample, or let's say your standard being the circle closest to the L axis. And then what you have is your LAB values for that standard, and then you have your LAB values for your sample that you measure. And what you see is their difference in your A, your difference in your B, and your difference in your L all get square rooted and give you your total delta E, which is your total color difference between the two. And that's usually what people use for their tolerancing. So some people, tolerancing can be anything. It's fully custom, but as an example, if you have a delta E tolerance of 1.5, anything under 1.5, you would say is passing, and so that product would pass. But anything over that difference of 1.5, that would be failing, and that's when you would have problems in your production or manufacturing. All right, so that was a nice quick overview of the basics of color theory. kind of explaining, how an instrument or an observer, how it all comes together, how we see color, why it works this way. It gives you a nice basic overview of the whole process. So with that, I'll give it back to John, and we'll get the questions.
Yeah, good job, Noah. As always, appreciate your insight and information. Yeah, folks, keep the questions coming. Just log them in the chat box and we'll get to them. First one of the year, Aaron. He's asking, is it better to observe at a 60 degree as opposed to a 10 degree? Maybe you can elaborate on that a little bit, and also go into when it's appropriate to use 10 versus 60 and vice versa.
Yeah. So when you say 60 degree, you might be referring to just the angle, typically 60 degrees for gloss measurement. And so some people do get confused a lot of times as 10 degree and 2 degree and 60 degree, 85, 20. What's the right one? Really, when you're talking about observer angles, it's not related to, specular gloss measurement where you typically have 25 or 20, 60 and 85 degree geometries. This is just referring to how your eyes are seeing, or what part of your eye is actually viewing an object. And so this is taken into the calculation for a color measurement automatically. It's something you can select on the instruments itself, but it's completely separate than the 20, 60, and 85 degree geometries that you'll see on some instruments for color and appearance. The 2 degree just refers to, what section of your eye is being used. So if I'm looking at something small like the letter of a keyboard, let's say, it's only using a small section of that eye. So the color correlation is not that great. For example, if I scaled that up, if I looked at a key on my keyboard, let's say it's a black key, and then I scaled that color up, it's going to look a little bit different than what I look through with, a small object versus if it was a very large object. They're not going to correlate the same. But if I was looking at something with the 10 degree observer section of my eye, so a larger object, I'm going to get a better correlation if I scaled that up bigger and bigger because it's using a larger section of my eye, if that makes sense.
Yeah. Maybe you can, do you have a slide in here that just shows the angles so you can see the difference between like 10, 15, 60, 45? And how that plays. I know it's in the gloss and appearance presentation.
Yeah, let me see if I can pull it up real quick.
Okay.
All right. Share my screen.
Perfect. We got some good questions in here, folks. So keep them coming. This is great.
All right. Can you see my screen?
Yes. Yes.
Okay. And it's on the slide here?
Yep.
Right?
Yep.
Okay. So this is an example of this is the gloss measurement geometry. So here you have 20 degrees and 60 and 85. And what this is referring to is how the light's being sent towards the object and then where the detector is to pick up the reflection of that. And so it's two different things that you're looking at. One being how your eye's picking up whatever you're seeing, and this is just how the light's being sent and how it's being picked up by an observer.
Perfect. And then how does, and I think this is back to the normal presentation, how does gloss impact that? Can you show that gloss absorption and diffusion slide again?
Yes.
keeping you hopping this first one.
Really quick.
Yeah.
So what was the question again?
How the angles play off of a gloss surface versus the absorption and diffuse.
Gotcha. Okay. So the angles are really they're really meant for specific types of levels of gloss. And so, something to think about is gloss is really dependent on the texture of a sample. So if you can imagine, this sample here is very flat. Obviously, we can't see micro texture on it because it's an image, but if you can imagine it's a flat, glossy surface, you're going to have more gloss in this case. And when you're looking at those measurement geometries for gloss specifically, not for color, but just for gloss, a 20-degree angle. Can you see my mouse at all?
Yes, we can. Yep.
Okay, so a 20-degree angle gloss meter. What that's going to do is it's going to send light like this, so at a very sharp angle down, reflect off the sample, and it's going to reflect back at a sharp angle. So a very sharp angle at 20 degrees here. And so if you have a very glossy surface, and you can replicate this by taking your phone out and even looking at your phone, if you look at it from a 20-degree angle, you're going to see a clear reflection because it's a very glossy surface. But if I had something that was more of a semi-gloss, that's when it's ideal to use the 60-degree angle, because the 60-degree angle is going to give you a better correlation for that. And so if you had something like a semi-gloss and you looked at it from the 60-degree angle, which is something like this, so we're coming down like this, and then it's going to be cast that reflection at the opposite angle of 60 degrees again. And so that's going to give us a better correlation if you were to have something like a semi-gloss. Now, if you had something like a matte surface, so something that has a lot of micro texture, and so it's not going to be glossy, it's going to be very matte. If you look at a matte object at an 85-degree angle, which is, very flat line here, so it comes down like this, hits the surface and gets reflected back like this, that 85 is going to show you the most reflection at that angle for a matte surface, if that makes sense. And so what you're really trying to find is the angle at which you get the most reflection for the surface that you have. That is typically the best angle to use for that sample. And so a rule of thumb is 20 degrees is the best for high gloss surfaces, 60 is the best for semi-gloss surfaces, and 85 is the best for matte surfaces.
Nice. No, thank you. That's good information. And, kind of related to that, how does the gloss or the surface texture affect the perception of color?
Another great question. Yeah. So if you can imagine, another great example is your phone. If you looked at your phone screen when the screen's off, it's a very glossy surface, and it's going to look like a very deep black. To the contrary, if you looked at the same exact color, but it had a lot of micro texture on it and was matte, I'm looking at my phone case right now. It looks like the same color, but it's a matte surface. It's going to look a lot lighter because what's happening is all this light's coming down and it's being scattered across the surface because of the micro texture. And so it's going to make it look whiter. And so a matte surface is going to have a lot more lightness. So your L value is going to be higher. And a glossy surface is going to have a lot, all that reflection, all that white specular reflection is going to go off in one direction. It's not going to be scattered around the surface. And so when you look at it, it's going to look darker. And so you'll have a lower L value. If that makes sense.
Yeah, totally. Next question here from Jason. Can you explain the differences between Delta E Star, Delta E 1976, CMC, and Delta E 2000?
Yes, great question. So Delta E Star was one of the first equations. As you can see, it's a very simple equation. The problem with this equation is that it's set up in a way to where it's, very, let's say, boxy or very square. Or the problem is our eyes don't see perfect. And so this equation doesn't take into account, the differences in how we see different colors. So, for example, our eyes don't see a lot of differences in greens as much as they do in reds. For example, if you had very vibrant reds next to each other, we could easily tell the differences between the hues. But if you had a bunch of greens that were slightly different next to each other, we visually wouldn't be able to tell those differences. And what delta E makes is it creates a box tolerance system, if you can imagine, to say, if this color is next to this color, and if it's off by this much, then we physically wouldn't be able to see a color difference. Or if it's off by a little more, then we'll be able to tell that color difference. The more advanced equations, like you mentioned, delta E CMC or delta E 2000 being the newest one, those they're a lot more complicated equations, and they help to take into account how our eyes actually see color. Lots of more testing was done, lots of more experiments were done on how humans perceive color. And so they take into account all of that. And so overall, when you look at the delta E equation, it's not, it makes it to where every color has the same tolerance for our eyes. But the newer equations make it to where each individual color has its own tolerance depending on where it is in color space. And we have a great presentation on that. I don't know when we're doing it this year, but we have a couple YouTube videos up for the last ones that we've done. And it's a very thorough presentation. It goes over all the specific differences in the equation, what that looks like, in the real world, how you apply that. And it's a very informative one. I think it's definitely something to look into if you have a question like that.
Yeah, I just in webinars like this and in previous ones, we keep all of these recordings and archives on our YouTube channel. I just put the link in the chat. You can copy that and look for what we did last year, or do a search. There's lots of other things there as well. So good stuff. Let's see. Next question here. Please explain the 45-0 versus sphere significance. And I'll add to that, Noah, are there any industries or applications that have standardized on one versus the other?
Yes. So to start, 45-0 is, let me get to this one here. 45-0 is similar to this setup here. So if you can think, what is 45-0? The light source is coming in from 45 degrees, hitting the surface, and then your observer, whether it's a person or a spectrophotometer, is directly overhead. And so what you're doing in this case is if you think of the gloss, which is that pure white light, we don't care about the gloss because we want to look at the color. And so the gloss in this case is hitting the object and going this direction, which means our eyes are going to see purely just the color without the influence of that gloss. A good example is if you're looking at a magazine and you're trying to read, if you're looking at it in a way to where the reflection of the sun, or let's say a lamp next to you, if that lamp's going and reflecting the light right into your eyes, you can't read what you're trying to read, right? But if you tilt it a little bit, or if you set it up in a way where it's 45-0, where your light's coming from 45-0 and you're looking directly overhead, or your light's right overhead and you're looking from 45 degrees, because you're not getting that spectral reflection right into your eyes, that's how you're able to see the color. So 45-0 is similar to this setup here, where a sphere is so it's very different. Your measurements aren't going to correlate. Again, we have a great presentation on this one too, where we go over when to use it, why to use it, and how to use it. A sphere is essentially, if you can imagine a white sphere that's coated in white, and it sits over top of a sample. as you take a measurement, what's happening is your light is not hitting the sample directly. It's actually diffused light. And so in 45-0 geometries like this is a direct light source hitting the object that we're trying to measure. Whereas in a sphere instrument, you're using diffused light. So your light's coming in from the side and it's hitting this white coated surface, the sphere, and bouncing around until it eventually hits the sample and illuminates the sample. And then the reflection of that sample is then scattered through the white sphere until it hits the sensor inside of that white sphere. I know that was a lot. Like I said, the presentation we go over has visuals for what I just said, and it's a lot nicer to listen and look at. But the big picture is they don't correlate. It's two very different type of measurement systems. One's using direct light, one's using diffused light, and so you're not going to get correlating results with that.
Yeah, and I'm gonna another link coming in the chat box here. It's a link to our white papers section. There's lots of new white papers specifically around color theory and things like this. So there's the link, wealth of knowledge there if you want to take a look. As always, too, we'll do what we can here on these webinars. We'll also follow up with you directly. Also know that the door is always open for you to hit reply to any of those marketing messages. We'll get it to the technical experts in your region to get your questions answered. Let's see, where are we? Okay, next question from Thomas. Can your device calculate delta E from one sample to another, measure part 1, measure part 2, report delta E?
Yes. Yep. And so that's like we referred to the example here. So, like you just said, you have your sample or your standard, and you're trying to get your samples to reach that standard. You take one measurement of your standard tile or standard sample, and then that's your target. And you take a measurement of your samples, and then the instrument will actually calculate that difference for you and display it in real time. So you can see it on the floor. And then you can also put it into our software, and that'll export it into a PDF, and then you can have a nice report set up with that too. So it's a nice instrument with, it gives you a lot of resources to be able to visually see if something's passing or failing right there and then, but also go back and report on that later too.
Yep, exactly. Another question, can you extrapolate translucency tinting levels using the Spectral 2 guide?
Yes, so the Spectral 2 guide does have an opacity mode. So if you have a chart or some paper that has a white side and a black side, and you can keep that consistent, you can put it in this opacity mode. You can do it right on the instrument itself. It has in the settings, and it'll ask you to take a measurement of, let's say a blue sample over the black side and then over the white side, and then it calculates the opacity based off of how it can read through and read the differences of the base color.
Okay. Good stuff. Let's see what's next. Jose's asking, what type of raw material or primer, where applied to the coat, can change the final top color for delta E or visually?
That's a good question. I'd have to say it could be a lot of things. It's hard to generalize that question, just because a lot of industries have a lot of different technology that they put into coatings, and it could really be a lot of things. But delta E is really your total color difference. And so if you have, let's say, a primer that's going down, and then you have a base coat that's has a high or a very low opacity, and you can see the primer through that. The primer is definitely going to play a role into that. It's really you're looking at what are the influencing factors in your total color difference, and whatever you can see is changing that, if that makes sense.
Yeah.
And that could be clear coat, that base coat, primer, it could be really anything, even substrate. Just, substrate can have texture on it, and that texture can play a role into the gloss. Then you can try to fill that in with clear coat. But, a lot of variables at play there.
Okay. Yeah, makes sense. And we can follow up with you directly as well, Jose, on that to find out specifically about your application and how we can assist. Another question. Refer to the difference between delta E and E2000. This means our eye perception is more accurate to notice different red shades than green shades.
Yes. So let me put it a different way. So if you imagine delta E, what this is doing is it's equally weighting the L, the A, and the B values together. But let's say, you have a green color, and you can clear the way our eyes see green. I mentioned it before, is our eyes have a hard time differentiating differences in green. And so what that means is your greens can have higher tolerances than your reds. Okay? And so if you want to make a universal tolerance where you don't have to go in and run all these different visual tests to figure out how well your eyes are seeing something, these equations are meant to create that universal tolerance for you. And so an example would be, I have a tolerance set to 1.5, meaning anything over 1.5, I can visually see that difference in color. Anything under 1.5, I can't tell a difference. And if I look at the greens and I have it set to 1.5, what will happen is, let's say I have a whole set of colors here and they're all green, and I measure a bunch of them. I can have ones that are falling outside of that 1.5 tolerance, and I'm throwing those away because they're failing numerically. But if I were to go back and look at those samples, I would find out that almost 50% of them are actually passing because I can't tell a difference between them. But numerically, because my tolerance is set low on the delta E, I'm failing all of them. Whereas if my tolerance was set at 1.5 on our red colors, right? And I took a bunch of measurements of red samples, and I found that, they're all passing numerically. But if I went out and looked at each of those samples, I might see that, they're all different. I could tell easily, I could physically see that they're all slightly different than each other. But numerically, my delta E is saying they're all passing because I'm using delta E star and it's not weighting where they are in color space. And you see what delta E 2000 does is it'll figure out where you are in color space. So if you're in the red region or if you're in the green region, and it'll make that tolerance smaller or it'll make that tolerance bigger, depending on what color you're actually looking at. And so if I'm looking at a red and using delta E 2000, my tolerances are physically going to change to make them a little bit tighter so that I'm not accidentally failing samples, or vice versa. And so that's really what the equations go into.
Okay. Ooh, we're getting deep. It's January. You guys, let up. All good stuff, though. Yes, we are. Okay, couple questions here from Larry. How does the 45-0 angle relate to 2-degree, 10-degree observer angle? Okay,
so again, they're different things that you're looking at. So 45-0 is just how the instrument is set up to take the measurement, similar to a gloss measurement, whether it's coming at 20 degrees or 85. It's just the way the light source is set up and the detector setup. Whereas when you're talking 10 degree and 2 degree observer angles, when you say observer angles, that's referring to what section of the back of the eye is being used. It's not something that's really talked about much, because for the most part, almost everybody uses the 10 degree observer. The reason being is because, pull it up, the 10 degree observer uses the rod cells and the cone cells. So it's a larger section of your eye. And we find that the rod cells also are important for color evaluation, whereas the 2 degree observer was used in the 1930s and before, when it was thought that because there's a higher concentration of these cone cells that are color detectors in this small little section, this must be the best way to observe colors and measure colors. But it's not true, because it's not taking any of the rod cells or our lightness detectors into account. Mm-hmm. It's only looking at the cone cells. And so historically, everybody used the 2 degree observer, but since then, more science came out and more information was released. And so people began to switch to the 10 degree observer, because that actually makes sense. It correlates well to what we're seeing visually. There are still some industries that use the 2 degree observer for specific reasons, some being historical data, some being a correlation to what they're measuring, and some that they measure smaller things, or they're looking at color differences in smaller things, like in the printing industry, when you're just looking at the colors of the letters, right? Because it's a very small thing that you're looking at, our eyes, when we look at that, are only going to use a very small section. It's not going to use the whole section. Like the example, if you're looking at a quarter, it's only using the 2 degree section of your eye. If you're looking at something the size of a tennis ball, it's only using the 10 degree observer. So for the most part, you won't hear it much that people are talking about the 2 degree and 10 degree observer, because it just goes to how our eyes looking at something. But it is a setting on an instrument. But it's important to know it's completely separate than the geometry in which the instrument measures.
Okay. So just to clarify, so the 45-0 versus sphere measurement is regarding the light source, and the 2 degree versus 10 degree is the observer. Is that correct?
Yeah.
Perfect.
That's a good sum up.
Nice. Thank you, Larry, for that. Yes, you are correct. Another question here. Normally, the customers consider delta E shall be 1 or less versus the master or standard. Is this acceptable? Is it a different value depending on the color or the application? Maybe you want to touch on tolerances. Yeah,
it's a good question. So with delta E, and then with delta E, that's your color difference. But with that, it's important to know what equation that you're using. For delta E star, that was the first equation that came out. That was 1964. And with that, it's not the most accurate. As we went through time, there was new developments in the 70s, and then in the 90s, and then now it's in the 2000s. And each time it got more and more accurate to actually measure and record that color difference as the human eye actually sees it and perceives it. The equation for, I can pull it up. I might actually, let me see if I can share my screen real quick and give an example.
Sure. And one of the great benefits, of working with us, we have technical sales reps around the country, around the world. So if you need someone to come in or to do just a virtual meeting, we have lots of folks able to do that, to assess, what your applications are, what you're trying to do, where you're running into some hiccups, and we can help iron those out for you. To get you, as efficient and as precise as we can.
All right.
Well, that slide gives me a headache.
So this is the equation for delta E 2000. As you can see, it's a lot more complex because there's a lot of things happening with our eyes and how they're actually perceiving color. And so this is what's interesting, but we see it's all weighted. And what that means is your L, your C, and your H are weighted. What this equation actually does is once you get to a chromatic color, because our eyes can easily detect differences in pastels or achromatic colors, or light grays or beiges, we can easily see those differences. And so that means there's tighter tolerances there. But when we get more chromatic, like a fire engine red or a fluorescent orange or something, those colors we don't see differences in chromaticity as well. And so this equation will actually switch between LAB or LCH depending on how much chroma is measured. On top of that, it was found that when we look at blues, it's not as uniform as when we look at other colors. So, it actually shifts the tolerance angles for the blues slightly in the specific region of the blue section. This gets really deep into it, but it shifts it because we see blues slightly differently. And so this takes that into account. Whereas when you look at the other equations like delta E, pull that up here, very simple equation. It doesn't weight anything. And this is where you can have a shortcoming where all your difference in this case, you have difference in your L, A, and B. This is equally different. And so when we look at the standard versus the sample, it's fairly close. It's under 1, or it is 1 exactly. Whereas this one, because I'm using delta E star, I could have all of my difference just in our A value, which completely shifts the color, but it's still 1. And so technically it's still passing, but it's not visually. What these advanced equations do will change depending on where you are in color space. So let's say now, because this is all of our differences in A, now it's 1.0 in the A, it'll now think this is a purple. So now it's going to say, hey, this is completely out of tolerance.
Yep.
And you can see it here, a lot of different equations for a lot of different things. But to sum it up, delta E2000 is now the most accurate one, because this sees, or this not sees, but this will develop a tolerance for a color based off how our eyes actually perceive all of the colors around us. And so I think going back to the question that you had here, do this, pull up this again. Let's see.
Are you looking at the questions or?
Yeah, I had to pull it up there.
So they're down. It's down.
You asked, consider delta E shall be 1 or less versus the master. So with color, a trained colorist or someone that's spent their whole life looking at colors and measuring colors and understanding differences, a trained colorist can see, I believe, around a 0.5, whereas the typical person, a difference in delta E of 0.5, whereas a typical person, like a regular person that doesn't really get into all this color theory stuff, they'll see a difference above a 1.5. So typically, I think, I don't want to say standard because each industry has different standards, but typically a 1.5 is sufficient for some people. But if you want tighter tolerances, a 1.0 is pretty sufficient. Anything under a 1.0 is start to get really tight, and you really can't see a difference, below a 1.0 unless you're a very, very trained professional colorist, and this is what you do all day, every day. But for the most part, if you're making consumer goods or something, a normal person is not going to see differences below a 1.0.
Yeah. 2 more questions. We're going to hang in there. If you need to drop, go for it. You'll get a link to the presentation shortly. So let's see, 1 point UV varnishes can shift a color to the yellower side. Is that accurate?
Yeah, for sure.
Okay. We got the expert confirmation. Thank you. And thank you, Jason. Last one from Timothy. Would you normally set tolerances higher on the dominant hue axis, LAB tolerances, and not delta E?
If you want to get really specific with your colors and you want to limit out shifts, you would set that. But typically, especially with the newer equations, you can just set what tolerance you want your delta E to be at, and then it'll automatically weight the LAB tolerances. And so because of that, you can't have a case where something only changes in the A and it's still passing, right? If it changes in the A significantly with the newer equations, it'll weight that into the equation itself and change your delta E accordingly. So for the most part, you can just set the tolerance on the delta E, but if you really wanted to get deeper and hone in on your tolerances, you could set it on the L, A, and B values and on the L and this or the hue and the chroma values. But it's not necessary with the newer equations.
Nice. All right. Well, thank you. And one final comment here. Someone's asking, is it possible to activate a closed caption option on the webinar? And I think we use Click Meeting, and it's coming out of our mothership in Germany. And I was just looking around. It doesn't look like it has that option. I'll investigate. Alternatively, I do take the video file and run it through a transcription system. So I do have the transcripts of that, and that's I put a summary and the key points and the time codes in the YouTube description where I'll post this. So that may help if someone would like a free or the full transcript. Just shoot me an email or reply to any of the marketing messages, and I can get that sent out for you. But this is a great one to start the year off. Looking forward, I think next month we have appearance theory, which goes kind of hand in hand with this color theory presentation. Thank you all for attending. Glad to see you engaged. Glad to have you here, and we look forward to seeing you on future Bitgardener web seminars. So thanks, and have a great day. And thank you, Noah, for all your input and expertise.
Thank you. Take care.